Okay, in 5.2 we're going to be discussing independent and dependent events. And the question is, how can you determine whether two events are independent or dependent? Well, let's look at the definitions first. So two events are independent events when the occurrence of one event does not affect the occurrence of the other event. Two events are dependent events when the occurrence of one event does affect the occurrence of the other event. So, determine whether the events are independent or dependent. Two six-sided dice are rolled. Well, they're independent of each other. They each roll on their own, correct? 6 pieces of paper, numbered 1 through 6, are put in a bag. 2 pieces of paper are selected one at a time without replacement. So think about that. If I take number 1 out first, that changes the probability for whatever number I'm going to pick next. So those are dependent events. So in this section, you're going to learn how to determine if they're independent. We're going to find probabilities, and then we're going to talk about conditional probabilities. So two events are independent if and only if the probability that both events occur is a product of the probability of the events. So we can use this formula here to decide if they're independent, but we can also use it to find the probability. So this is the probability of independent events, and it's calculated this way. If these are not equal, by using the sample spaces, then they are not independent. Okay, the first thing we're going to do is use a sample space to determine if two events are independent. So a group of 4 students includes 1 boy and 3 girls. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. Use a sample space to determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. So the first thing I'm going to do is put all the information out there so we can go through it one by one. So these are all your possible outcomes. Okay, this is girl 1. There's only 1 boy, so he doesn't have any number. This is girl 2. This is girl 3. So these are possible outcomes where there's only 1 girl chosen. Okay, these, girl 1, girl 2, girl 2, girl 1, these are the possible outcomes that have 2 girls chosen. Now, these are the ones that we want because we wanted a girl first and then a girl second. So if we look at the probability of a girl being first, there are 12 possible outcomes, and we can see that there are 3 here and then 6 down here. So there are 9 possible outcomes. So girl first would be 3 over 4. Okay, then we're going to look at the possibility of a girl being chosen second. So look at this one. This is where a girl is chosen second. So these 3. And then in all of these, a girl is chosen second. So again, the outcome is 9/12, which reduces to 3/4. Now what we're going to do is look at the very specific one, girl first and girl second, and there are 6 of those possibilities. You can see them right here. So it's 6 out of 12 equals 1/2. So now we're going to use that formula, the P of A and B. So these have to be multiplied together. So this is the P of A and B. And this is the possibility of A times the possibility of B. And these have to be equal for it to be independent events. And since they are not equal, they would equal 9 over 16, which does not equal 1/2. The events are not independent. Okay, so that's one way to use that formula. Okay, so first thing we have here is we have some problems, and we have to determine whether independent or dependent. So you have 3 white balls, so white, 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 and 2 yellow balls, yellow, yellow. And you randomly select 1 golf ball to hit now and put another one in your pocket to hit later. Use a sample space to determine whether randomly selecting a white golf ball first and then a white golf ball second are independent events. So I'm not going to put all the possible outcomes, but what I can look at is if I pick a white one first, the probability is 1 out of 5. Once I've taken that ball out, the probability of getting a second white ball would be 2. There's 2 left, but out of a total of 4. Okay, so this is 2 out of 4 because I've already taken 1 ball out. As soon as you know that you're taking 1 ball out, you know that it is a dependent event. But I'm going to put this and show you mathematically. So what we want to know is what would be the white? We don't know, but we know that as soon as this bottom number changes, that means that they're dependent events. Okay? So there you go. All right. Your friend writes a phone number down on a piece of paper, but the last 3 numbers get smudged after being in your pocket all day. You decide to randomly choose numbers for each of the 3 digits. So you're choosing numbers. You could choose 1, 2, 3, 3, 4, 5, 1, 1, 1, and it doesn't matter what number you choose first, that's going to make the second number. You can choose randomly each time. So since each number you choose is not dependent on the number you chose first, this would be independent. Okay? So look at the explanation here, and that will help you understand how to do these choices independently. Okay. All right, so now we're going to find the actual probability. Remember, the formula is the probability of A and B equals the probability of A times the probability of B. Okay, so as part of a board game, you need to spin the spinner, which is divided into equal parts. Find the probability you get a 5 on your first spin and a number greater than 3 on your second spin. So right away we know that how you spin on the first one is independent and how you spin on the second one are independent. So we can use this formula. So we're going to go the probability of A, so that is 5, and there are 8 outcomes, and there is 1 5. So that's 1/8. Okay? And then we can find that the probability of greater than 3. So B is greater than 3, and there are 1, 2, 3, 4, 5. So that would be times 5/8. Okay, so let's look at the work that they did for us. So here we go, 1/8 times 5/8, and you would multiply that out, 5/64, and equals 0.078 or 7.8%. So any of those answers would be correct. Okay, so there you go. Okay, so the probability of dependent events. If 2 events, A and B, are dependent, then the probability that both events occur is the product, meaning multiply, of the probability of the first event and the conditional probability of the second event given the first event. That's what this symbol means here. So it's B given that A already happened. That's what that symbol means. Okay? So if we're going to go back to the example we did before of the girls speaking, so the first thing is the probability of girl first. So we found that one by the probability of girl first. There were 9 out of 12 of those. So that's the probability of girl first. In order to look at the second one, we're going to take how many of them had girl first. Okay, so look at girl first. There were 9 girl first, and so that becomes the denominator for this one. So girl first, and then what was the probability of girl second? Given girl first, there was 6. So that is how you find the conditional probability. Then you multiply them, and you would get 54 out of over 108, which would reduce to 1/2. So stop this, push pause if you're not sure about this, but think about it, think it through before you go on to make sure you understand. Okay? All right. So find the probability of dependent events. So the bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, and then randomly draw another bill from the bag. As soon as they say you're setting one aside, you know these events are dependent. So find the probability that both events A and B will occur. So event A, the first, is that the first bill is 100. Well, we know there are only 5 out of the total of 25 bills. Okay, then the second bill is 100. Well, the first thing we have to know is that the second bill out of 100, we now have only 24 bills. Okay, we took one away, and there's only 4 $100 bills left. And you could reduce that if you want. Okay, so that is a quick way to remember how to do this. And then we put that together. So they showed us here. See, I don't always need the whole chart to do that. I could do it in my head like I just did for you. And then we get the probability of that given that. Okay, so there you go. So the probability that you draw 2 $100 bills is about 3.3%. All right, so now we're going to compare independent and dependent events. So you randomly select 3 cards from a standard deck of 52 playing cards. What is the probability that all 3 cards are hearts when you replace each card before selecting? That would make them independent, okay, because we're putting it back each time. Or B, you do not replace each card. That would make them dependent. Okay, so let's look at those. The formulas for finding probabilities of independent and dependent events can be extended to 3 or more events. So, the first card is a hard, the second card is a hard. So, we know that there are 13 hearts in a deck of 52. So that is, the first card is a heart. We're putting the card back. So the second one is also 13 out of 52. And then it's 13 out of 52, correct? So we're going to multiply each one of those. And we're going to get this formula, okay? All right. Then for B, we're not replacing it. So the first heart, it's 13 out of 52. But the second heart, there's only 12 left, and there's only 51 cards left, right? And then the third heart, there's only 11 hearts left, and there's only 50 cards left. So we have to subtract one from each time. So if we're going to calculate this one, it's going to look like this, which is a much bigger number and a much smaller probability. So now we can compare them. So you're 1.2 times more likely to select 3 hearts when you replace each card before you select the next card. So you take the first probability and divide it by the second probability to figure out the difference or to compare them. Okay? So know what you're doing each time, whether it's independent or dependent. Okay, these 2 problems are from your journal. Page 165, and you are trying to guess, so push pause if you want to try them on your own, otherwise we're going to go through them. So you're trying to guess a 3-letter password that uses only the letters A, E, I, O, U, and Y. Letters can be used more than once. Find the probability that you pick the correct password, Y, O, U. So the probability of you getting the Y correct is 1 out of 6. Since you can use any letter in any combination, the probability of you getting the U correct is 1 out of 6. And then the probability of getting the U correct is 1 out of 6. So you multiply that out and you get 1 over 216, which equals 0.0046, and the answer is about 0.46%. Okay, and number 4, you're trying to guess a 3-letter password that uses only the letters A, E, I, O, U, and Y, but the letters cannot be used more than once. So find the probability that you pick the correct password, A, I, and E. So the first thing we look at is we know that if we get A right, it's a 1 out of 5 possibility. A 1 out of 6, sorry. 1 out of 6 possibility because there are 6 letters. But then, when we go to Y, there's only 1 I, but there's only 5 letters left. And then to get E, there's only 1 E, but there's only 4 letters left. So now we multiply that, and we get 1 out of 120, and that equals approximately 0.0083. And so there's the probability that you would get that correct. Okay? So it's harder to get the 3 letters when you have no restrictions than it is to get them correct if you have restrictions. Okay. Okay, so this problem shows you how to use a table to find conditional probabilities. So a quality control inspector checks for defective parts. The table shows the results of his work. Find the probability that a defective part passes. So the first thing you're going to do is go to the defective parts, and you find the total, which is 39. Okay, so that is your total. All right, and then the probability that it passes, only 3 defective parts passed, so that would go here, and that would give you this. Okay, then it says find the probability that a non-defective part fails. So non-defective parts, there was 461, so that becomes your denominator, and only 11 of those failed. So there is the probability that a non-defective part fails. Okay, so think about that. You can rewrite the formula for the probability of dependent events like this. Okay, so think of that and look that over. Okay, so now we're going to try it on our own. This is number 5 on page 165 of your journal. Okay, so if you need to go to that. So first thing we want to do, find the probability that a randomly selected collegiate soccer player is a female. So we're going to go to the soccer players. We're going to find the total number of soccer players, and that is 73,763. And now we want to know what percentage or what's the probability that one of those is a female. So we're going to put the female number on top, divided by the total, and that is approximately 4.4951. Okay, and so we're going to look at the answers when we're all done. Then find the probability that a randomly selected male, so now we're going to look at the males, randomly selected male student is a collegiate basketball player. Now in this one we've got a problem because the book said it wrong. So it should say athlete, because these are actually both athletes. Now there are going to be students at the college that don't play sport. So that they made a kind of an assumption here, but they totaled it and they said that this total was 69,103. So to calculate this one, my total is 69,103, and then we're going to put basketball 31,863, and that is approximately 0.46109. So you can see our answers up here were correct, but again, like I said, they made they made the wrong assumption here where they said a randomly selected male student. So they should have said soccer or basketball player is a collegiate basketball player. So be careful how they word these. They'll usually be much more careful, but I noticed that when I was doing this problem, and so we just had to make the assumption that they meant out of these ones that were looked at. Okay? All right. Okay, this last problem, it's giving you the answers, and you have to figure out what part of the formula they are. So at school, 60% of the students buy a lunch. Only 10% of the students buy lunch and dessert. What is the probability that a student who buys lunch also buys dessert? So this buys lunch is our denominator, and this would be our numerator. So now you have to look at these figures and figure out what that is. So this is showing you how to do that. So this is the probability. The numerator is they buy lunch and dessert, and the denominator is they buy lunch. And this was given in the information. 60% of our students buy lunch. This is the percentage that also buy dessert. So we can calculate the probability right here. So use these problems to do your homework tonight and make sure that you understand how to go over each of these things. Okay.